Hey y'all, welcome back. In this video, we're going to be talking about other primitive type variables. So far, we've talked about int, which can store integers, double, which can store decimals, and boolean, which can store either true or false. But there are many other primitive type variables. For example, byte, short, and long. Notice on the right side that all of these store integer type values. You'll also notice they have different memory sizes, 8, 16, 32, and 64. And on the right side, you can see a range of values that each variable type can store. This range depends on the memory size. In another video, I go over what a bit is, and I won't cover that in this video. We also have what is called a float. Notice how it is 32 bits, and it can also store decimal values. So it is a cousin to double. And then we have something called char, which is short for character. Notice it is 16 bits, but it's unsigned. I go over this in another video where I go over binary representation and 2's complement. But again, the only ones you need to know for the AP exam are int, double, and boolean. I think though that knowing what a character is would definitely help. So let's talk about this stuff. I live in Texas, and in Texas we have something called HEB. We like to say it stands for Here Everything's Better. So if you remember from the previous slide, a float is 32 bits and a double is 64 bits. Again, I like to think of these variable types as containers. We've talked about boxes before, but remember we said that decimal values are like liquids, right? So here we have a 32 ounce container, a 1 quart container of milk. And here we have a half gallon container of milk, 64 ounces. I chose these values because a double is 64 bits and a float is 32 bits. Now imagine both of these were empty and you were trying to pour water from one to another. Could you pour 32 ounces of water from this container into the 64 ounce container here? Yeah, right? No spills if you have a steady hand, and no problem. But imagine if you had water in this half gallon container. Could you pour it into this 32 ounce container without it overflowing? No, you couldn't, right? The water would overflow. 32 ounces would be in here, but then all the rest would be outside of the container. So that leads us to a rule. A smaller container cannot hold a larger container. And we make it a smaller variable cannot hold a larger variable. Okay, so let's go ahead and see that in action. We'll get to that in a second. But we also want to talk about integers and decimals. Okay, so we talked about how each one has a different size. It's represented by a different number of bits. So why would I ever use a byte or short variable type? And remember, byte or short is 8 bits or 16 bits. When I could just use an int or a long variable type, which is 32 or 64. Why would I use 8 or 16 instead of just using 32 or 64 all the time? Similarly, why would I ever use a float when I could use a double? Well, this goes back to more olden times when memory size was very important. So for example, imagine you're writing code to bring aboard an International Space Station. There's very limited memory and storage capacity. You want to be as efficient with memory as you can. So when memory or storage is limited, you want to be very careful with how much memory you allocate to each variable. However, in our class, and with really any computer you use nowadays to program, feel free to use only int and double. And that's what College Board expects you to use. However, please be aware of memory limitations in real-world applications. If you start writing programs in C or for microcontrollers, typically microcontrollers are limited in memory size and what they can store. So again, for more specialized pursuits, you definitely need to be careful of memory. So let's go ahead and take a look. Remember from our last video, we had this error from trying to assign a double to an int because this is a decimal, it can't go into an int. And our analogy was hey, you can't put liquids inside of solids. I'm gonna go ahead and make a new class right here. And I'm gonna comment this out so I don't get those red crisscross lines over there. And this one I'm going to be calling other primitive. There we go. I'm gonna open it up. I'm going to delete all this. And I'm just gonna show you the error you get when you try to put something that's larger inside of something that's smaller. So here, I'm gonna make a, let's make a short. Let's make a long. Big value. All right, big value is gonna be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's do that. Now, if you remember, this is 1 billion, right? So 1,234,167,890. What is the range? Let's go back a couple of slides. What is the range of an integer? Or let's just say a byte. It's only -128 to 127, right? So can I put all of this inside of here? Can a byte accurately represent a long? What do you think will happen? Will I get an error? So this compiles, but if I do byte small value equals big value, and I try to compile it, this is essentially assigning a long variable, right? Because big value has been declared as a long, assigning it into a small value. And I don't even need to click compile, but I click compile and I see I get, hey, incompatible types, possible lossy conversion from long to byte. So let's go ahead and comment this out. And actually, let's comment out this way. Okay. So I'm going to write a note up here. Cannot put long into byte. Let's go ahead and try it the opposite way. So can I put a byte into a long, or an into a long? So let's go ahead and do a short. Short value, I guess, equals 1, 2, 3, 4, 5. Let's do 1, 2, 3. I think that's within the range. And I do int value equals short value. Can I put something that's less into something that can hold more? And yeah, no problems. It compiles. Okay, so hopefully that shows you proof that you cannot put large into small, but you can put small into large. Now, I also want to talk about a character. So to designate a character, you use a single quote or the apostrophe to designate a character. For example, you have the variable type, variable name, assign value, and we have the capital A inside of the apostrophes. And then we declare another character variable type called letter A, and we assign the letter number. This is a number 65. And when we print out both of them, when we print out letter, we get a capital A, and we get print out letter A, which has the value 65. We also print out a capital A. Wait, what's happening? Right, what's happening there? If you don't believe me, you can go ahead and prove it to yourself. Okay, so char letter. You know, sometimes I'm known to lie a little bit to see if my students are keeping track. So again, I'm assigning the value of this character, capital A, to letter. I'm assigning the value of 65 to letter A. Sorry, I mean to say I'm assigning the character A to letter, the variable, and I'm assigning the value of 65 to the variable letter A. Compile. I'm going to go ahead and run my code. And you see A's print out. So I'm not lying. That's good to know. So what's happening? Why did printing out the variable letter A, which if you remember was assigned the value of 65, result in printing out an A? Well, in Java, character variables are actually stored as integers. That's how they're actually stored. If you remember from a previous slide, all right, right here we have 16 bits And what it stores, if you look at this column, it stores an integer from 0 to 65,535. So it's actually stored as an integer. So look back at the other slide where char letter is assigned the value of a capital A. This is actually storing the value of 65 in the variable letter. What Java does is when we print line the letter or print line the letter A, it sees that we declare those variables as the char type. And so it converts that integer 65 into its character equivalent. Now, what do I mean by character equivalent? And how do I know that a capital A is character equivalent of 65? Well, if you go online and search an ASCII table, you can find the decimal heading on this table and you'll find the number 65. If you follow horizontally, follow the row, you can find the character equivalent. So you can practice doing it yourself. If so, pause this video, go look for an ASCII table, try to do what this slide is saying. But I've also done it for you. So this is an ASCII table from wikimedia.org. And if we find the decimal column, so decimal column, we go to number 65. We go horizontal to the char column. There's letter A, capital A. Okay, because if you look at the lowercase a, that has a decimal value of 97. So you can use this ASCII table to understand what the decimal equivalent is of a character. Okay, so these first two lines of code should be familiar. These were on a previous slide, but now we do capital A plus 3. So remember, capital A is an integer. This is a character. Okay, notice the single quotes. That's a character. We add 3 to it. Well, what is 3 more from 65? 6, 7, 8. And the character equivalent is capital D. Okay, so when we print out letter, remember, letter is a variable that has been declared as char type. It's going to see that letter is storing 65, but then it's going to know, oh, letter is a char type. I'm going to print out the character equivalent. So it prints out capital A. Similarly, when I print letter A, it sees that letter A has been declared as a char type. So even though letter A has been assigned 65, it's storing 65. Once again, it sees that it's been declared as a char type, so it finds the character equivalent in 65 and it's capital A. For letter mystery, we did the math and we know that capital A, which is 65 plus 3, is 68. The character equivalent of 68 is a capital D. Now, the last two are a little bit different, right? So what is capital A? The decimal value for capital A is 65. Now, what if I add 3 to it? Well, it's 68. Wait, Mr. Wang, what's different between that line 3 code and this one? Well, if you notice, letter mystery is being declared as holding a character. So when I print out letter mystery, inside of letter mystery is the value 68. But because I'm printing out letter mystery, which has been declared as holding a character, it's going to find a character equivalent and print out 68. In this line of code, I'm just adding 3 to capital A, which is 68, and printing it out. And the last one is very similar. When I divide capital A, which is 65, by 5, I get 13. All right, I hope this helped hopefully show you some other primitive variable types. Again, the only ones you need to know are int, double, and boolean. But I do want you to be able to learn more as you see fit. So hopefully this was helpful. Maybe it helped explain some things. And as always, let me know what you thought about this video. Do you have your own analogies you'd like to use? Do you need additional help with this? Give me some feedback. You'll find a link in the description below. See you in the next video.